In this video, we're going to talk about AVL trees, which are height balanced or self-balancing trees, okay? And the problem they're addressing. So we talked about, and I do have my Apple Pencil back, so my drawing should be better. We talked about the efficiency of a search in a binary tree that looks like this, okay? Basically, if we search at this term, and if we find out that what we're looking for is smaller than the root, okay, then we know we can immediately get rid of all that, okay, which gives us at the big O of n log n, which is good, okay? But this efficiency only works when we have balanced trees, okay? And the example in the other video, I showed that if you were to insert the numbers sequentially, okay, so you insert a 1, then a 2, then a 3, then a 4, and then a 5, and then so on, there's no balance to your tree at all. Okay, so any advantage that you would have from the binary tree is gone. It's just a linked list. Okay, and this is at a big O of n, basically. Worst case, you have to do all of the elements. Okay, so there have been several strategies people have come up with to fix this problem, to make sure that the tree is being balanced, okay? So we start with this concept, and it's the only one we're going to cover in any detail, although there are others, is going to be for the AVL trees. The AVL trees are named for the three guys who came up with that, Addison, Valesky, and Landis. So two guys, sorry, one had two names, okay? So we're going to talk about this, some concepts here. The first one, we're going to talk about the tree being perfectly balanced. Okay, so perfectly balanced would say that the height of the left tree and the height of the right tree are equal. Okay, and that the left tree and the right tree are also perfectly balanced. Okay, so we have an issue in trying to make all trees perfectly balanced, in that we may not have the right number of elements. Okay, so if we have a tree that looks like this, that's perfectly balanced. If we're going to add 1, there's no way to add 1, no matter where you add it, either there, or there. There's no way to add it in any of those places that are going to make it perfectly balanced. Okay, so that is too stringent a requirement. Okay, so in the AVL trees, we're going to instead search for this. Okay, we're going to say that if the tree is an AVL tree, then first off, the height of the left tree and the height of the right tree differ by at most 1. So we're allowed a little more wiggle room there, okay? And then the second, as we've seen before, LT and RT are also AVL trees. So this has to go throughout the entire tree, okay? There's no way for it to fall apart later, okay? So example of AVL trees, if you have, one here, one there, 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 okay? So in this case, the height of the left tree, that's the longest link, is 1, 2, 3, 4. Height of the right tree is 1, 2, 3, okay? So that's okay. Okay, then of course something like this, like we did before, this is not okay. Okay, so we can further talk about the following terms. Okay, if we have, let's say, T is an AVL tree, and X is a node in T. Okay. We can also talk about the height of the left and the right here. Okay. So if the left side is bigger, so if LT is bigger, we call it a left high tree. And if the RT is bigger, we call it a right high. Okay. So we have to make sure that if this is off by more than one, so if this distance between the left and the right, okay, is more than one, then it's going to violate the balance criteria. Which means it has to be no more than one. Okay. So what this means for us when we're creating an AVL tree and we're looking at the node, okay, it's going to look like we've looked before. We're going to have our templating stuff. You don't have to have a template, but it makes sense to do so. With our class and our element type. Okay. We're going to have a struct. This is going to be an AVL node. Okay. An AVL tree is a binary search tree, but it has extra criteria. Okay. So the struct here is going to have the element type info as it has before. Okay. But it's going to add this int called B factor. Okay. And that denotes the balance factor. Okay. And it's this balance factor that always, it can be either a -1, a 0, or a 1. If the balance factor goes beyond those three values, then we're going to have to rotate and change our tree. Okay. And then of course we have our AVL type pointer for left link, and then AVL node type pointer for R link, like before. Okay, so as we're going through this, we're going to have to make sure that we calculate this balance factor. Okay, so basically the way it works, when we go to insert, okay, into an AVL tree, okay, since it's an AVL tree, we can assume before the insert that the balance factor is either a -1, a 0, or a 1. Okay. After we do the insertion, then we have to make sure that that balance is still there. Okay. So, for example, if we have the following tree, we insert a 50, we're good. We insert a 40, it's going to go here. It's a binary search tree. Okay. So the left height is going to be a 1. And the right height is going to be a 0. So it's just a difference of 1. So we're good. Okay. And say we do a 70, it's going to go over here. Now they're equal, which is good. Okay. Now we do an 80 over here. Okay. And we're still in the balance factor is still okay. In this case, it's at a -1. So it's 1 minus 2 or -1. Okay. But it's only when, if we added a 90 here, that we have a problem. Okay, now the balance factor, when we insert the 90, we're gonna have to do something different, okay? And the something that we do differently is depending on how things look, okay? But, and there are four possibilities. So in this case, what we're gonna do to keep this in balance is we're going to basically promote the 80 and put the 70 there. And now we're back in compliance, okay? So we refer to these as different rotations. Okay? And there are different ways that we can do this, okay? They're called left rotation, right rotations are the most straightforward of the rotations, okay? So when we look at the left rotation, okay, for an example of that, we're going to have to, it's when we're out of balance, okay? So rotate to the left, okay? So if we have, and I always get the left and right wrong until I do them, okay? So if we entered a 1, a 2, a 3, for example, okay? This is out of balance because we have more on the right, okay? This one's gonna be right heavy, okay? So to fix this, we're going to do a left rotation, okay? And that's going to become the 2 on top, the 1 here, and the 3 there, okay? So that is the left rotation because it's moving to the left, okay? Which means a right rotation, if we have a 10 to 9 to 8, okay? The right rotation is the 9 rotating to the right to give us the 9 on top, the 8 over here, and the 10 over there, okay? So that's our right rotation, okay? And then there are other times when it's not that straight line that we're looking for, okay? So there are times when we're going to have to do a left right or a right left, okay? So if you have something a little more complicated, so if you have a 1, okay, let's look at that. If you have a 10 that goes to a 20, okay, that goes to a 15, okay? When you have a crook in it like that, okay, you have to do 2 different rotations, okay? So what you're going to want eventually here is you're going to have to pull the 15 up to the top, okay? So you're going to end up with a 15 and a 10 and a 20, okay? But to do that, you have to do 2 rotations, okay? So the first rotation that you're going to have to do, okay, is to do a left rotation here to get rid of that problem. So you're going to go the 10 to the 15 to the 20, okay? You can then, okay, no, that was actually, is that a right or a left? I get left and right confused. Your next step, though, is going to, oh, that, sorry, I just don't know right from left. This is a right rotation. Okay. You now do a left rotation, that to that, which gets us to the 15 on top, the 10 over there, and the 20 over there. Okay. And then the opposite problem would be if you had something that looked like this. Okay, so this is a 10, this is a 5, and that's a 7. Okay. Again, you would start by doing a left rotation to give you the 10 to 7 to 5. Okay. And then a right rotation to give you the 7, the 5, So you do this on the insert. So at the end of every insert, you're going to have a balanced tree. Okay. So again, we have a left rotation, we have a right rotation, we have a left right rotation, and we have a right left rotation. Okay. Depending on how things work. Okay. And again, you know, if it's in essence a straight line of nodes, you're doing either a left or a right. If it's crooked, you have to do the left, right, or right, left. Okay. So hopefully that's clear enough. Okay. When you're deleting something from your AVL tree, you still have to worry about whether or not the tree remains balanced. Okay, sometimes if you're deleting a node that was the only thing keeping it balanced, then you're going to have to rebalance things. Okay, so what this AVL tree does, and there's always trade-offs. Okay, so as far as the AVL tree trade-offs, okay, on the positive side, you're always nearly balanced. Okay, so you're never off by more than one in the left and right subtrees, heights. Okay. The con, though, is that you may have processing to do at every insert. Okay. And when you have a big enough tree, when you insert something, you make sure that it's locally balanced, but that can throw off the whole tree. You can have a lot of side effects. You can end up having to do a lot of rotations. Okay. So this means that your search times are going to remain constant, but your insertion time could be worse. Okay. So some other alternatives just to throw out. Okay. We have what are called 2-3 trees. Okay. And what the 2-3 tree does, it tries to defer having to do the reorientation. Okay. By basically allowing each node to have 1 or 2 bits of information. Okay. So if we have a 10 here, we have a 5 here, and we have a 20 here. Okay. If I go to add a 30, we're still relatively balanced, but if I go to have a 40, we're not. Okay. So what it would have done at this point, when we go to add the 30, it would go ahead and put a 10 and a 20 up here. Okay. So it would do that to defer the time it would take to have to reorient things. Okay. So there are also things which we won't talk about called red-black trees. And it's just another strategy to avoid or to delay having to go through the rotations. Okay. So we can now take a quick look at the coding involved for this. Okay. Won't go into great detail, but I will put it out there in the temp directory. So let me stop the share there. Leave the meeting there because we're done with that for now. Okay. Should be able to look at the code here. That's the terminal. Kick me off. They kicked me off. So let me pause this for a second. I'll get back on. Okay, I'm back on now. Just kicked me off. Okay, so let's take a look at the header file here. Okay. Got the AVL Treedoffs. So as we saw before, we're just adding this balance factor here. Okay. Then we have our insert, as you would expect. Okay. we have our rotate to left, rotate to right, balance from left, balance from right, the insert into the AVL tree. Then we have our inner order traversal, we have our pre-order traversal, and we have our get balance factor, and then a search, then our constructor. Okay. And again, we have our in order and pre-order. We're doing those functions as private functions that allow us to call just with no parameter, then call the others. Okay. So I think that what is probably most interesting. Okay, let's see here. There's the search. The search should work more or less like a normal search. Here are rotations. If I missed the insert. Maybe I missed the insert. We'll see. There's the insert. Okay. So on our insert here, okay, we're again going to insert. Okay, we're sending along a node we're going to call root. Okay, and we're sending on a new node. Okay, and then this Boolean is taller. Okay, to our insert AVL. Okay, so with this one, we're going to go through and check to see if the root is null. Okay, if so, we're going to go ahead and go through that. If not, we're going to call the insert into AVL again. Okay, we're again looking for if the root info is bigger. Okay, so whether it goes to the left or the right tree. Okay, and then we're going to check to see if we need to do some rebalancing. Okay, then we'll either do the balance from left. Okay, else we're going to go through here, balance from right to make sure that works. Okay, here's the generic insert. Here we go. Okay, so we're going to insert the new item, and then once we've created the new item, okay, that's when we then call the insert AVL. It then calls that and make sure that it's properly balanced. Okay, so I'll put this code out there that you can take a look at, but it's worth understanding graphically first how this works, and then how we're going to get the code to be able to do this. Okay, so again, this is an important concept for us in that this will ensure that our searches are always right at that n log n space. Okay, so there's much else here. AVL test. Yeah, I just did this one with some inserts. Okay, and this one, assuming I haven't compiled this one today, so there may be an issue, maybe not. Okay, I don't know what it's printing out, but it should, when we're inputting the numbers sequentially from 1 to 100. Okay. Oh, it searches for 34 and returns a tree. That's all it's doing. But yeah, you could go through it and show, you'd have to go through and do a traversal at some point to see how it's doing it. Okay, but that should be balancing it every time that it goes through. Okay, and if you're inserting it sequentially, there's going to be lots of balancing for it to do. Okay, so that should do it for this. So again, plenty to look at there. So make sure that you go through the code, and if you have any questions, make sure you let me know.